All right, welcome to Recitation for exam number 3, which is over chapter 17, Acids and Bases. And today what we're going to do is just cover 5 problems that are representative of some of the types of calculation-based problems that you might encounter on the upcoming exam. Now, remember that this isn't inclusive of all variations on these calculations, and you're still going to need to be versed on fundamental definitions of acids and bases. What are weak acids? What are strong acids? What is pH? What is Ka and Kb? And what are the relationships between Ka, Kb, and pH? So you're still going to want to practice, get back into the homeworks, and review a lot of your definitions and a lot of your relationship type questions, in addition to these calculation-based questions. So, like I said, this recitation is going to cover a couple of the calculations that are representative of the kind of problems that you'll be seeing on this exam. So to start it off, problem number 1, let's see if we can find the concentration of hydronium ion in solution if that solution has a concentration of hydroxide equivalent to 1.8 times 10 to the negative 5 moles per liter at 25 degrees Celsius. So now that we've said it, let me see if I can write this down, some of the highlights. So what we want to do is find the concentration of hydronium in an aqueous solution, and where we know the concentration of hydroxide is, let's see, 1.8 times 10 to the negative 5th moles per liter, or that could just be written as molarity. And this, of course, is at 25 degrees Celsius, so that our relationships are valid in these equations. Now, there's a couple different ways you could approach this. And I'm just going to show you one of the approaches. But the first one approach that you could use is you could find the pOH of the solution. Since you know the concentration of hydroxide, you could use the relationship that the pOH equals the negative logarithm of the concentration of hydroxide ion. And then once you found pOH, you could use the relationship that pH plus pOH equals 14. And then once you've found pH from that relationship, you could go back into our concentration relationship between pH and and concentration of hydronium, where pH equals negative log of the concentration of protons or hydronium. We can use that interchangeably in this equation, and that would give you the concentration of hydronium. So that would be one approach. However, I think there's a more elegant approach, which is the one I'm going to use to solve here. And what I'm going to do is just use the relationship that Kw is equal to the concentration of hydronium times the concentration of hydroxide. And this makes for a very, very simple solution for us, because instead of going through all the different manipulations that would get us a perfectly valid answer, we can just rearrange this equation so that we're solving for a concentration of hydronium, and then we'll just take Kw over a concentration of hydroxide, and Kw is going to be 1 times 10 to the minus 14 at 25 degrees Celsius, and we can substitute in our concentration of hydroxide, 1.8 times 10 to the minus 5th molar, and when we do this solution, that'll give us 5.5 times 10 to the minus 10 moles per liter. Slick. Okay, so that was problem 1, our first example. Let's see here. Let me scroll down a little bit. It's not letting me scroll. There we go. Room for problem number 2. So problem number 2 is going to be, let's find the concentration of hydronium, or free proton, in an aqueous solution where the pH is 4.33 at 25 degrees Celsius. So this is actually, I'm going to use this equation that we just referred to, but first I'll write down the question. So what we want to do is find our concentration of hydronium, or free proton, in an aqueous solution where the pH is 4.33. And this is going to be at 25 degrees Celsius. So right away, I think what everyone's going to gravitate to is an obvious relationship. pH equals negative log of concentration of hydronium. So once we have this relationship, we're probably pretty adept at just, if we have the concentration of hydronium, finding pH, but there's a little bit of math involved in going the other direction, which is what we're being asked to do here. So what we're going to do is we're going to just substitute in and then do a little adjustment. But generally, what you would do here is you'd multiply both sides by -1 and say negative EH equals the log of our concentration of hydronium, and then we would raise both sides as an exponent, and this is going to eliminate the log and give us our concentration of proton. So what we can do here is say our pH is 4.33, and we have a negative log of concentration of an unknown amount of hydronium that's responsible for this pH. So we're going to multiply both sides by -1, eliminating the negative from the left side of the equation. And then we're going to raise both sides as an exponent, tenfold exponent, and our concentration of hydronium is going to be equal to 0.00047, or 4.7 times 10 to the -5th power moles per liter. As you do more of these, when you see this relationship, what you'll probably do is just move the negative and raise it to an exponent automatically. But showing your work and keeping track of your steps is always advisable. So that is our second problem. Let's see here if we can. Let's see here. Oh, it's not letting me do that. Okay, so what I'm going to do is I'm just going to get rid of the footer, hopefully. Oh. Always fun to change things up a little bit, isn't it? All right, now that I figured out how to get rid of that and reset, problem number 3. So problem number 3 is, what we're going to do is try to find the concentration of hydronium ion in a solution where we know the pOH. And in this case, the pOH is going to be 8.85. So given we have a pOH of 8.85, what we want to do in this scenario is relatively elegantly find the concentration of hydronium ion. And there are a couple ways you can do this. The one approach is to find the concentration of hydroxide directly from the pOH, and then you can substitute into a relationship of POH to pH using kW, or in this case 14, and that would look like this. You could just find, oh, I have no idea what's here. What on earth? I've never had so much difficulty. There we go. Identifying what on earth is going on here. Okay. Now we're back in it. So what we could do is, why is this keep going away on me? Let's try this again. Okay, so POH equals the negative log of the concentration of hydroxide. And once you've solved for the concentration, or found the concentration of hydroxide, you can then use the relationship that Kw equals concentration of hydroxide times concentration of hydronium, and you'll get your solution that way. Alternatively, what I like to do is just take the relationship, which, because I think this is more elegant, that POH plus pH equals 14. And I think this is a clearly more elegant solution, because all you have to do to solve from this perspective is rearrange the equation to solve for pH. So in this case, 14 minus 8.85, which gives you a pH of 5.15. And now that you know the pH equals negative log concentration of hydronium, and you can just move the negative, raise both sides to an exponent to eliminate the logarithm, and that would look like concentration of protons, or in this case hydronium, equals negative 5.15 raised to 10 the exponent, and this gives you 7.1 times 10 to the negative 6 moles per liter hydronium ion. So that's going to be our third problem. And like I said, there's what you're probably seeing here is that there's often a variety of correct ways to solve the problem. So knowing your way around these relationships really facilitates problem solving in general, because you don't have to have a specific algorithm which gets you to a solution. There's a variety of approaches that you can arrive at naturally. That doesn't mean that they're all as elegant as each other, and so having a variety of approaches often lets you solve the problem more quickly, because you'll have your choice of a few different approaches, one of which will be better than the others in terms of speed. Doesn't mean you're going to get a different answer in the end. And oftentimes, if you're in a tricky situation, it's reasonable to solve it twice, using different approaches to validate your answer. So, that said, I'm going to just erase this time, try to avoid the complications. Bear with me, could have been doing this while I was talking about approaches and all that. And this seems silly on the internet, but if we were on a whiteboard, I'd be standing in front of the whiteboard with an eraser doing all this manually, and it'd take about the same amount of time. So, problem number 4. But that wouldn't be happening on a whiteboard. Problem number 4. Let's make it a little bit more complex now. Let's go and determine the Ka of an acid which has a concentration of 2.94 moles per liter in aqueous solution and a pH given at 2.8. So let's say we've got, let me write this down. What we want to do is we want to find the Ka of an acid. And this acid has a given concentration of, 0.294 moles per liter and a pH of 2.80. So to do this, we're going to have to lean on the relationship that defines Ka, which is when you have a weak acid, which is partially dissociating, just like an equilibrium constant, where you're going to look at your products over your reactants. And your products in this case is going to be the concentration of hydronium times the concentration of your conjugate base over the concentration of your undissociated acid. And we can get to one of these directly and two of these indirectly because we have pH. And we know how the relationship between pH and concentration of hydronium works. So all we need to do first, as a little subplot here, is say, using the relationship that pH equals negative log the concentration of hydronium, state that the concentration of hydronium is going to be equal to 10 raised to negative 2.80. And this is going to give us a concentration of hydronium of 0.00158 moles per liter. Excellent. So now that we know this, we've got our first part. But not only do we have the first part, whenever HA dissociates, I can write this out, and remember that free proton H plus is equal to hydronium when it complexes with water, which because of its large excess of water in solution. So this is equivalent of, if we were to write it with water on the reactant side. But this isn't important in terms of arriving at the correct answer. Just a little bit of shorthand. Because of this one-to-one dissociation we see, if I know the concentration here, I simultaneously know the concentration here, and they're equivalent. So the concentration of hydronium equals the concentration of the conjugate base. So we can set up this relationship to say Ka is going to equal the concentration of hydronium, which is 0.00158 moles per liter squared, because it's 0.00158 moles per liter hydronium times 0.00158 moles per liter conjugate base. And then we have to divide by the amount of weak acid that remains. And we know what we started with. We started with 0.265 moles per liter. And due to dissociation, we lost whatever X is, in this case, 0.00158 moles per liter. And we can just finish this calculation where we get, this is going to be a little bit long, I don't think I need to write it out, but just square the top and you'll get 0.000025, and then you divide that by, you know what, I'm sorry. I grabbed the wrong number here. That doesn't make any sense at all. Let me scroll up. 0.294. There we go. Now we're talking. 0.294 minus 0.00158 is going to be 0.293. It's just gonna, if we're doing sig figs. And regardless, we can solve this and get 8.5 times 10 to the minus 6 as our Ka. So this will be our correct solution for this particular problem. All right, let's go ahead and do a little bit of erasing here. I wonder if I can just go all, oh, that's so much more elegant. Excellent. So last problem of today. Determine the concentration of hydronium in a weak acid, HClO, with a concentration of 0.265 moles per liter, given a Ka of 2.9 times 10 to the minus 8. So what we have is we have this weak acid at a concentration given of 0.265 moles per liter and a Ka of 2.9 times 10 to the minus 8th. And what we want to do is find the concentration of hydronium, or free protons, in solution. So the way to approach this is to go right back to our definition of Ka. So Ka is going to be our concentration of hydronium times our concentration of our weak conjugate base over our concentration of our non-dissociated weak acid. And what we know is our Ka. Ka in this particular case is going to be 2.9 times 10 to the minus 8th. We also know our concentration of our initial concentration of HA before there's any dissociation. That's going to be 0.265. What we don't know is the concentration of either our hydronium or a conjugate base, which are equivalent. So what we have to do is we have to treat those as variables x, and then we need to square them and then remove that equivalent amount x from HA underneath. And what that's going to look like is 2.9 times 10 to the minus 8th equals x squared over 0.265 minus x. And this is where you have the opportunity to save yourself some time, because you could rearrange this and use the full quadratic equation to solve. However, you don't have to, because we have sig figs in play. And what we're seeing here is that if x is much, much, much smaller than 0.265, it's not going to significantly change it. So you don't have to include the full quadratic. You can use an approximation. In this case, our our x is going to be quite small, and we can check that at the end. But this is going to be approximately equal to x squared over 0.265. This is a much easier solution and faster solution than using the full quadratic, because we could just multiply both sides by 0.265, leaving us x squared. and then just take the square root of both sides, and x is going to be 8.8 times 10 to the minus 5 moles per liter. And if x is that means that the concentration of hydronium is also that. Now, if you're concerned about this, note that 8.8 times 10 to the negative 5 looks like 0.0000088. And if you were to subtract this term from 0.625, it will not alter those three significant figures, and therefore cannot alter our answer. So this term for a concentration of hydronium is small enough, because the acid is weak enough, that it won't significantly alter our equilibrium concentration of our weak acid, and that means we can use this approximation successfully. Now, if it were to alter that number, we would have to use the full quadratic to make a solution, but in this case we don't need to. So that's going to wrap up our fifth example. I'll put the number there, and I think does a pretty good job of representing the fundamental operations which you'll need to be making throughout the exam, and there will be variations on these things as well, and you might be asked to do some extra steps, like for instance identify a strong acid or strong base, make the leap to know what that means in terms of concentrations of protons or hydroxides. You may be asked to take information relative to these and calculate a percent dissociation, for instance. There's a couple other variations on the theme like this, but this I think does a pretty good job of pointing you in the right direction on the kinds of manipulations you'll be expected to make over the course of this exam. So that's all for today, and I hope it's helpful. Study hard, make sure you get back, review those homework questions, and good luck with the exam.